So good afternoon, everyone. My name is Francesco Petruccione, and I'm the interim director of NITheCS. And welcome to this, I think, this fourth lecture in our August mini-school dedicated to machine learning methods for high energy physics, for particle physics. Yeah? And today, our lecturer is again, like last week, Dr. Xifeng Ruan from WITS University. And he started last week to give us a very practical session on how to analyze these data sets from high energy physics using machine learning methods. And today he will continue with the practical demonstration and practical instructions. And next week, Professor Bruce Mellado, who is also with us this afternoon, and who will kindly keep an eye on the Q&A facility and moderate the questions. He will give us the last lecture in the course next Tuesday, which will be probably more dedicated to big data and maybe some more theoretical aspects of this topic. Yeah. And sorry, and among the panelists, you also see, like almost every webinar of NITheCS, Professor Ilya Sinaisky, who always kindly agrees to be the co-host in case there is some issue with my internet or whatever. So he has always the rights to keep going with the webinar. So he's our canonical plan B. Yeah. So thank you, Ilya, for that. So Dr. Ruan, if you are ready, we can start. And sorry, I always forget the usual reminder to the participants to use the Q&A facility or maybe to raise your hands if you want to ask a question. Yeah. So Xifeng, if you are ready, we can start. So thank you very much for your second lecture.
Okay, thank you, Francisco. So thank you everyone for attending this second part of this hands-on session. Before we start, I'm going to do some recap. That's what we have done last week. So as I suppose that you have opened that this notebook, so that everything is there, that we haven't changed anything here. So from last week that we spent quite a lot of time just to describe how to and how the data set looks like and how to have some say the pre-analysis of the data, that we know that the data set usually is just like two dimensions. So one is one dimension is like to show the different roles, that is the different individual independent events, and the one dimension is like the features, also the variables. So usually we say the features. It tells you that for a single event you have different feature and with different value. And then last week that we also have a look at all of the distributions of these all of the events for different features, like the maximum mean and this percentile and the statistical statistical properties. And then we also draw some one-dimensional histogram to have a rough feeling that how there's difference between the two data sets. We call the signal and background. So because we have to have some differences between the signal and background so that we can separate them using the machine learning. But of course, now we haven't used the machine learning yet. We just have a rough feeling that, for example, this distribution, that the blue signal is more on the right side and the red background is more on the left side. And for different features, their distribution, they're different. Some of them, like this one, has quite a large discriminant power, that the overlapping region is relatively small. But for some of the variables, not that obvious, like this one. Okay, and then last week, we also just introduced the concept of the correlation, that the one-dimensional histogram that gives you some information, say the difference between the signal and the background. But it's not enough. It's not all of the information. So we also need to consider the correlation between the feature to feature. And you can see that if you calculate the correlation between, like say this PT gamma gamma and the missing T significance feature, they are different for the signal and the background samples. So the machine learning is something like it can exploit that the correlations between the features that between the signal and the background is much stronger than simply just cut on the one-dimensional histogram. Because if you use one-dimensional histogram, you don't need machine learning. You just make a simple selections. Is the left is signal, right is signal, left is background. Then you can roughly separate the data set. But using machine learning, you can do it more effectively, because it can explore more differences between the two data sets, more information. Yeah. Then last week we just entered that this part that is more technical issue, that how to build the data set and then label them the signal, label them background, and just merge them to one single data set. Then split the data set to be the training and the test data set.
From the
So
CFO of health,
excuse me. So
by her formal position, she is in a supply chain, but she was brought in to manage.
Bruce, could you please? Yeah, thank you. Okay, so here what we are doing is that we split the data set to be the training and the test part. And later I will explain that why we need the test data set. This is extremely important. If we don't have the test data set, we can have anything and all kinds of the result which is unrealistic. Okay, so here that we set the test size 0.5. That means it's 50% randomly. 50% of the data points, the rows will go to the training. 50% will go to the test. So we will only use the training data set to train the models, the machine learning classifier models. So here, and last week that we have introduced this a bit. So this is the training models that we are going to use to split the signal and the background. So here we introduced the actually it's two different classifiers, also the models, but three of them. In one of this model, we split to three individual models which use the three different set of the hyperparameter. So the two models, one of them is the decision trees, or say the random forest, and another one is this multi-layer perception and machine. It's like it's also given a name, the DNN, deep neural net. So for we use this model for comparison. So for the random forest, that because that we know that for random forest, what we care about is the number of the depths of the when you build the trees, when you split the branches, and the number of trees in the forest, and also the other setup. Yeah. So here we just try different setup. We have the 400 number of trees, the 2 layer of the depths, and the 20 trees, 2 layer of depths, and the 800 trees and 4 layer of depths. So here what we introduce is 3 different set of hyperparameter. Is the purpose is try to let you know later to see that how is the performance of this different hyperparameter. And for comparison, we also put the MLP, that's also DNN method here, which uses 3 layers. With each layer, we use 30 nodes. Okay. Then what you are doing is that you can just run. If you just open your you just reopen this notebook, you can just press this button, so it will just run from the beginning to the end. So you don't need to click one by one. You just click here, and then all of these blocks will be run from the beginning to the end. So you see this is started. That means it's still running or not till here yet. Once this is to the line number or the block number, then that means it's finished. So because all of the previous one is not very complicated code, so it will run very fast. You see it's already here. Yeah. So here, I think this part is running because telling you there's a CPU time. So last time that we mentioned here is this first 2 lines that show the CPU time that we used for this first method. And the second block is the second method. And this is the third method. And this long list iteration from 1 to 29, it just shows the iteration that to train the train the DNN, and this loss as the value of the loss function, this has to be smaller, and finally stop somewhere. Okay, so finally it takes some time. So you can compare that how much time it takes. For example, for the DNN, it's like 4 seconds, and the first random forest method is also like 4 seconds, and the second one is only 200 milliseconds, and the third one is 15 seconds. So we can know that the second random forest method, which uses the least CPU time, that is because it only trained like 20 trees and only 2 layers of depth. But this is the third one, which use 800 trees and the 4 layers of depth, which gives you which consumes a much longer time. So that means at least we haven't looked at the results yet, but we already know that if you set more complicated numbers, for example, here, if you use the DNN, you use like 10 layers, and each layer you use 200 nodes, that will consume a lot of time. So the more complicated that you set up for the hyperparameter, that you use more CPU time. So this you have to have some compromise. For example, sometimes your analysis is really simple. You really don't want to have like a 0.1% improvement, but you take the whole month for the training, right? So yeah, this is just some kind of feeling that how the complexity is related to the training time. But of course, that this is also related to the complexity of the data set. If you have like 100,000 million of events and 1,000 variables, that will be also consume you a lot of time, and also depends on your machine. If you're using the CPU or GPU or just very fast the computing farm, that will give you different training time results. Okay, now here in this block, the block 24, here what we are doing is trying to calculate that also evaluate the test sample. Because just now what we have done is just we put the training sample in the classifier so that it will optimize all of the parameters, like all of the weight that in the DNN, or all of the weight that in the random forest. So after training, that all of the weights, they are fixed to some, will be saved in some file, and so these values will be fixed. Then this step, what we are doing is that we input the test sample again. So before, you have to be careful. Before we are using the training sample, we use the training sample to train, to fix the classifier. Now what we are doing here is that we use the test file, we use a test sample, and we use the already trained classifier to classify the test sample. That is like to do some scoring, or say to mark the test sample. For each row, each events in the test sample, the classifier will read in all of the features in the test sample and calculate a score, and then put the score, so label the score into each event in the test sample. So we can say that before that, the test sample has all of the features, and also because that we know the test sample is created by ourselves, so we know that each event is a signal background. But the classifier will use all of the features to recalculate a score for each event. And then in the end, what we can do is to compare that score and our already labeled signal or background label, try to see how accurate that score it is. So here, what this line is doing is actually calculate the probability from the score, from the prediction. So the probability will tell you that it is, so basically that this value is between 0 and 1. So it depends on the machine and your software. So we can always normalize them to be between 0 and 1. So that you can, later I will show you. So that if it's close to 1, that means it is more signal-like. If it is close to 0, it will be background-like. So each single event, it will be labeled a probability like 0.9, 0.7, 0.2, 0.3. So it's not saying that each single event will be 100% a signal or 100% background. It just gives you a probability. It's more signal-like or more background-like. So here, basically, we just redumped some data sets and to label that each single events a probability. So to tell you that if there's more signal or background like. Then let's try to have a look at them, how how it looks like. So here in the block 25, what we are doing, we just draw that the distribution of these probabilities. So we make several figures. So this one is for the first decision tree of the random forest method, and the second random forest method with different hyperparameter, and the third one with different hyperparameter, and the last one we use this neural net DNA method. Now, if you run this block, and you can see that's output here. So still we use the same color code, that is the blue color, that means the signal, and the red color is the background. And you will see that what I mentioned, that every single event is given probability, which is close to 1.0. That means it's more signal-like, which is close to 0, then it's more background-like. So then you can see the distribution of the real signal and the real background. So here blue, that means a real signal. It means we already know that this is a signal. And this every single blue event which is located in different places, it is to say, it tells you how the classifier tells you that it's more signal-like or the background-like. So the full description is like a real signal. It looks like a real signal or look like a background. A real background, it looks like a signal or a background. So you can always have some confusion, like this side, the blue real signal, but actually the classifier tells you it actually looks more like a background. This is always, this can always happen, okay? It can always happen. So then how to understand that this figure? So obviously what we hope is that we can find some places, for example, 0.2, we make a cut on 0.2. We say every single event which is smaller than 0.2 will be background. Every single event which is greater than 0.2 will be signal. If all of the signal events, which are the classifier labels them, give a value, a score value, which is greater than 0.2, and in the same time, all the background events will be given a value which is smaller than 0.2, then we can say that the signal and the background, they are 100% separated. They're 100% separated. It's like a blue ball and the red ball, you can easily 100% separate them, right, by the better color. So that is the ideal case. That of course that will not happen that very often that in our daily life. So in our daily life, what you will see is just like this figure. You always have some confusion or some mixture. So some real signal events go to the left side, be labeled as background, and some real background events will be labeled as signal to the right side. So the purpose of this figure is trying to separate the signal and the background as much as possible. Your ultimate goal is that you hope, but just hope, or you wish that all of the blue dots will go to the right side and all of the red go to the left side. But of course, that's just ideal case. So in general, that you always can allow a little mixture, but you hope that at least majority part, red dots will go to the left and blue go to the right. Now let's just try to compare different methods here. So you will see that the first method, you remember that it is actually an intermediate setup of the complexity of the hyperparameter of the random forest. So the first method, you can see it's like this. It's well separated. Most of the blue one is just above 0.2. And then let's just try to look at the second method. And you can see that we have a huge peak, blue peak, which is smaller than 0.2. And here we also have some events which is smaller than 0.2. So looking by your eye, that it's very obvious that you have more blue events, which is on the background side than the first method. That means the separation, also the discriminating power for the second method is not as great as the first one. Obviously, the first one just can do better job, right? So then let's just try to see the third method. If you see the third method, you can count that the leftmost bin, where the contamination from the blue color, which is a signal, shouldn't be here, is much smaller. So you can, if you read the y-axis, the number of normalized events is below 10. And okay, yeah, the first method, the second method is like above 15 on the left side. The first method we don't know because that the distribution is a bit flat. But if you looking by your eyes, it seems that the third method is slightly better even than the first method. Because if you see the red one, the red color for the first method, the first spin reached 40, and then you have some spread and up to 0.1 and reach 0.2. If you see that the third method, the first spin is reached to 50 and then significantly drop to 0 at 0.1. That means even we can just push the definition of the signal and the background from 0.2 to 0.1. We say every single event which is smaller than 0.1 is a background and greater than 0.1 is signal, right? So here we can say that the third method looks like, just look at the output distribution, the machine learning output distribution. We already can say that the third method is the best among the first three random forest method. The reason is very simple. It's just because the third method uses the most complicated hyperparameter. It uses 800 number of trees and also the 4 layer of the cut depths. You can see from here, the third method uses 800 and 4. And the first method is intermediate, it's the 402. And the second method is the simplest structure of the forest, random forest. So it's used 20 trees and 2 layers. So here you can have a feeling that the more complicated your hyperparameter set is configured, it seems like you have the best performance. Then possibly it's very easy to draw a conclusion. Then why not just I put a 30,000 number of trees and 30,000 layers? Can we just 100% split the blue and the red and we can have the best performance? Is that true? Then that is a question we are going to answer just in the next part. So first I'm going to stop here. So everyone, that if you find that with what we have introduced or you have any questions, you understand that the logic that I'm comparing these 3 figures to judge it which one is better than another. And if you get the conclusion, say that the higher, let's say the more complicated the hyperparameter, the better the performance to separate the blue and the red. So I hope that you understand this part. Okay. Okay. Just don't forget that we have the last figure, which come from the DNA method. But the DNA method, you can see obviously that the area that if you integrate that the left part below 0.2, the area of the blue signal sample is much greater. It's very obvious than this method and this method. And this method we don't know because we didn't do the integrals. So that means in such particular situation, the DNA method is not as great as the random forest method. But this is not always true. Not saying that the DNA method is worse than the random forest. The performance of different methods really depends on the configuration of your hyperparameter, the structure of your input data set. And for example, usually for high energy physics, for the particle analysis and the classification problem, the random forest ability sometimes is also in most cases is better than the DNA. But it also depends on how complicated your data set it is. It's not always true. Okay, so here what we put in here just for a comparison. So in such cases, it's not as great as the others, but this is lack of tuning. If you tune the hyperparameter, maybe it can perform better. Just tell you. Okay. Now we are going to move to the next part. Is that so? What we have done is that we have done the signal and the background separation. These figures, this machine learning output figures, it shows you that if the 2 color histogram, they are, so the distance between them, the further distance, the better. So that means the separation power is stronger. Okay. Now another problem is that, so here, it just shows that your separation power between the signal and the background, but we still don't know another very important property of the machine learning classifier is that the ability of the generalization. So the generalization that means now if we use a training sample, the training sample can be separated by the classifier well, and assume that we inject a test sample. We just mentioned a test sample before, right? We split the training test by 50 and 50%. So assume that we use a test sample because the classifier take no information from the test sample, because that and the classifier only use a training sample to optimize it and stop somewhere the optimization. But for the test sample, is like the classifier has no idea to how test sample is distributed. Assume that we evaluate the test sample. Will the test sample have the same performance as a training sample? This is a very important question to be answered. Also, the second question to be answered to describe the performance of a classifier. Okay, so in the block 26, what we are doing that we try to draw this. You see this PLT is just plot. What we are doing here is just to draw another set of plots to compare the output, the machine learning output distribution between the training sample and test sample to see that if the test sample reflects the same prediction as the training sample by using the same classifier. Okay, so let's just directly skip all of this code because it's just repeating and plotting. Let's directly see the plot here. This is the first method. And we are looking at the signal. So here we are comparing signal to signal. You inject the true signal sample, and you look at the test and the training sample. What you hope is that they should be identical or say roughly same. You can ignore these fluctuations because they're totally different data set. You can have some fluctuations up and down, but you should expect that the whole distribution should be roughly same. That shows that your classifier can work on the training sample and also can work same on your test sample. So that means you have a new total random data set. It will give you the same performance. Not saying that this classifier will only work on a particular a given sample. It can also work on any random new sample, okay? As long as the property of the new sample is the same as the training sample. So you can see that for the first method, that the comparison between the training and test, they are not perfect. It's not perfect. On the left side, that some test sample, they're supposed to be labeled as a signal or more signal-like. They should be on the right side, but they happen to show up on the left side. But assume that for the time being that we can tolerate this case. We say roughly that these two distributions still looks okay. They are compatible, but not perfect. Then let's try to see the, let's just skip the second figure. We just focus on the signal first. We look at the second method for the signal. And for this method, you can see that actually the green and the blue color, they looks very identical. Every single vignette almost the same height, except there's a few difference. So that means for the second method, the agreement between the training and test for your signal sample is almost perfect. That means that the classifier will treat equally for your training and any new random data set. Then let's just try to see the fifth figure, which is still the signal sample, but the training test comparison for the third method. You remember that in the third method, we put 800 random forest trees and 4 layers of depth, which is significantly more complicated than all other methods. Then you can see here that you have all of the blue color is on the right side. And all of the, no, half of the green color is on the left side. That means that you possibly, in your training sample, you can categorize 100% of your signal to your signal, but in your another random data set, you will label half of your signal to the background. So this is totally inconsistent. So this just tells you, even you use the third method, which is super complicated, not super, very complicated, and give you a very good separation power. You remember that if I just scroll up and you remember that this figure, the signal background separation is really very, very promising, very nice. But if you look at the ability of the generalization of the third method, you can see that for a new random test sample can falsely categorize the signal events to the background side with 50% probability. That's a very bad performance. So that means, though we set up a very complicated hyperparameter and obtain a very good separation power, but this classifier has an effect of the a lot of effect of the overfitting or say the overtraining. It doesn't have a very good ability to generalize that for the random data set. Okay. So this just tells us, answers the question we just previously asked. If it is the case that you use a more complicated hyperparameter, the better. So obviously here we already have one answer, is this not the case? So you should use as stronger as possible the hyperparameter, but in the same time, you have to keep an eye on the training test comparison to make sure that you don't see a strong overtraining. Otherwise, that your model can only work on your training data set or particular several samples, but will not be generalized to any new random samples. Okay, so here just give you a constraint, a limit to set up your hyperparameter. It's not the more complicated, the better. You have to stop somewhere to avoid that this huge overtraining. Then let's just try to look at the background distribution. So for the first method, the background distribution looks roughly okay. There's a little distribution here. And the second method is almost perfect. And for the third method, and you can see that, okay, just categorize the background in the very tiny bin that's on the left side, and this slightly different for the test sample. Okay, we have a question here. Hello? Hello? I see a question here. If you have any question, you can just speak. Okay.
Sorry,
yes. Okay, in case, and if you have a question, you can just stop me. Okay, so here we reach conclusion here. If you want to judge which classifier is better for your task to split your signal and the background, you have to at least consider two things, most important things. One is that separation discriminating power. How is the ability that you can separate the signal and the background? Of course, that as we shown that in the previous figure, that the distance is the larger distance, the better. And the second thing that you need to be careful is that assume that you already choose a set of configuration. I'll say your classifier is fixed. You need to check is that if your classifier do the same job for your training and test sample or for any new random samples. Okay. You shouldn't say that for the training sample, it has very good performance, but in your test sample, it is degraded a lot. And for any new random sample, it even has even worse discriminant power. So the discriminant power is totally dependent on how you choose a sample. That is something that you don't want. So basically, that here we can summarize that we have two things to keep in mind that to describe what is a good classifier. You have to have the best separation power, in the same time the least overtraining. Okay. But sometimes that we can tolerate a bit of the overtraining like this, the first method, if you can, sometimes you can tolerate a bit of this. It just depends on the task, how your tolerance it is. And then this is the last method, the DNA method, that you can see that because the separation power is not strong, so the overtraining is also not that strong. Okay. Then I'm going to move to one important figure that you always see. It's called the ROC curve, the receiver operating characteristic curve, shortened by the ROC ROC. So you can just skip that how the code is joined and it's just plotting. The ROC curve is that try to convert that this figure to be a signal and a background efficiency figure like this one. So what's the meaning? First, I'm going to explain what's the meaning of the ROC curve. So the x-axis, but sometimes in different article, different situation, you will see that they exchange the x-axis, it doesn't matter. So here we use the x-axis as a signal efficiency from 0 to 1. Signal efficiency is 1, that means after your classifier, 100% of the signal will be survived. It is like if you go back to this figure, I define a cut as 0.0, say any events has a ability output score which is greater than 0.0 as a signal. Any events is smaller than 0.0 is background. Of course, there's no events is more than 0.0. So it's like 100% signal will pass your cut, and 100% of your background in the same time will pass your cut. If you put, for example, 0.8, possibly 80% or 50% of a signal will pass your cut, and maybe 0.1% of a background will pass your cut. So on any point of the rho curve represent a given cut on these axes. 0, 0.2, 0.4, 0.6, 0.8, 1.0 will be the point on this curve. For example, 0.0 is here. That means all of the events will be labeled as signal. 1.0 will be here. That means all of the events will be labeled as background, and all other points will be just in the middle between these 2 points on the curve. So that represents the different efficiency that you select your signal and select your background. Of course, on the right side, that the signal background efficiency, both of them will be high. On the left side, the signal background efficiency, both of them will be low. So to here is 0% to label as a signal, 100% to label as a background. Okay. So I just mentioned that the x-axis of the rho curve is the signal efficiency vary from 0 to 1.0, depends on how much signal efficiency you label as a signal. And the y-axis is the background rejection. That means how much fraction of the background will be rejected, also will be labeled as the background. So of course, that the ideal case that you hope is that at this point, on the top right point, or this point, you keep 100% of the signal, you label 100% of your signal, and in the same time, you reject 100% of your background. This point would be the ideal point, the most ideal point that you hope that your classifier can do. But of course, in the reality, you always have the mixing, mixture, has the confusion. So you won't reach this point. You basically have some point which is close to this point, like here, or here, or here. Okay. So the purpose to draw the rho curve is try to use the rho curve to compare the performance of different method or different set of hyperparameter. Because just now we just directly look at this one dimension random forest output distribution, and we roughly judge which is better, which is not better, which is worse, right? So here we can use the rho curve, which will give you a much more precise comparison from method to method. So usually that we say that if one curve which is closest to this point, the top right point, then that means this curve is better. We also have some other criteria, for example, the AUC, the area under the curve. You make an integral that under this curve, like the yellow or the red curve, the greater this area, like this one, the 0.936, this one is 0.930. So the greater, that is the method is better. So this depends on your criteria. Not saying that you have to use you have to stick on one of the criteria. So it depends on your analysis. Sometimes, for example, if we don't care about this part, we only care about the situation where the signal efficiency, which is more than 30%, we only care about here, then we have to zoom in this area and to see that which curve is on the top. Then that means that method has the best discriminant power. So the rho curve is the very straightforward illustration that you can use to compare which method has the best discriminant power. But this one doesn't show you the at least that this figure doesn't show you the overtraining. You have to put the training and test rho curve together to show how the overtraining it is. Here, this one just to try to compare different methods. So you can see the MLP, the DN method that we just randomly set up a configuration. We didn't do any optimization, which has the worst performance because it's the lowest, has the smallest AUC, area under the curve. And then what we are going to focus is the first three methods, which use different, different number of trees and the depths. So the 402 depths, 220 trees and 2 depths, and 804 depths. And you can see that the red curve, which use the 20 and 2, which is obviously, very apparently, worse than the blue and what is the other color, the purple one. The purple one, yeah. So the red one is much worse, not much worse, just say inferior to the others. This is as our expectation, because we know that we set a very light hyperparameter. We don't set up a huge value here. And then if you compare these two, that the 402 and 804, so you will see that the performance actually, they're very alike. Or say even the two curves, they're identical. They have only a little difference at this place. If you look at the AUC, that even that the first one has slightly higher AUC than this one. It doesn't mean that this one is significantly better than this one, just say comparable. So with the help of this row curve, we can draw one conclusion here, is that as the first method and the third method, they have almost the identical, or say the same performance to discriminate the signal and the background. But the third method has such bad performance in the overtraining. So obviously we should choose the first method rather than the third method, because that we avoid overtraining, but we reach the same discriminant power, right? So this is just use the row curve to help you to choose the different method, different set of the hyperparameter. Okay. Till now that we almost reached the end of this hands-on session, we have the last block that this is just a part to do some automatic search of the best hyperparameter. For example, that just now we have analyzed that use different hyperparameter, different number of trees, different number of depths, that we can have totally different performance and totally different overtraining. But sometimes you wonder that I don't want to tune this value by hand, because sometimes you have like 10 different hyperparameters, a huge space, right? You want to automatically scan and let the system, let the computer tells you which is the best set of hyperparameters. So you don't need to do it one by one, change it by hand. So you can do some kind of automatic scan. For example, here we say the number of estimated number of trees. We can scan with from 100 to 1000 with a step of 100. And the learning rate, we can scan from 0.01 to 0.5 with a step of 0.05. Oh, I forgot which one is step, maybe the first many steps. And the max steps is at a different range. So then use this method, the grid search CV, it can automatically just run all of these combinatories of the hyperparameter, and it tells you that which one has the best result, okay, has the best score or something like that. Yeah. So this just tells you that you always have the automatic method to help you to do the search. And if in the reality that in actual work that you're facing a very complicated model, you have millions or billions of different hyperparameter, combinatories of different hyperparameter, you can just use a computing farm to do this, because the search is really, they can be calculated, they can be done in parallel. So you don't need to run it on a single machine. So basically the last part is just tell you that you can tune your model hyperparameter to help you to optimize the best separation power and automatically. Okay. So until now that we have done the hands-on session, I have a little additional material. But first, I'm going to ask if you have any questions that you don't understand for today's content. You can just raise your hand or just directly tell me. If no, I'm going to.
There's just one raised hand, Xifeng. I just allow the person to talk. Yeah. So Noko, you're welcome to ask your question.
Yes.
You just have to unmute yourself.
Prof, my question is on the last part on deciding which classifier is the best. So using this the grid search, so we can just on the grid search we can change all the the machine learning algorithm that we have used. We can just select them. It will show us the result, which one is the best.
Yes, exactly. So here, what I'm trying to show is just for the same method, but you are tuning the hyperparameter. You're choosing the different range of the hyperparameter. But of course, that you can, though I haven't put it here, you can just do some more complicated code to compare over different method from DNN to BDT to all other SVM, all other method, and try to decide which one is the best. This is a very brutal scan. There's no say principle here is to filter the method or the hyperparameter space in advance. So just a brutal scan tell you. Yeah.
So is this the question by Jeroen?
No, it's by no code. There are other
There's some questions on
using the random forest regressor. What do you mean random forest regressor? Actually, I'm using the random forest. What other kind of method would you use for regression method? Okay, you're talking about the regression method. Regression is a different task. So basically, we have the classification and the regression. Yeah, the classifier is to separate your events into different categories. You can now what you are giving an example of the two categories. One is signal and the background. You can have also 10 categories. And the regressor is like just to fit a value. For example, you have 10 input features, and it tells you that this 10 input features particular value has to be corresponding to output value. For example, like 8, just number 8. Okay, and then you want to train a classifier, the regressor. You can either use the BDT, the random forest, or using DNN, or using some linear one, or some or others. It's the same. So when you train that classifier, the regressor, when this regressor is already trained, the next time you just input another new set of the input features, then the regressor will directly return you the value. For example, assume that your training data set tells you this a particular set of the feature will return you a value 8, and the next time you put a test sample into it or validation sample into it, it should return you maybe a 7.5. So something like that. So the regressor will just try to calculate the relationship between your input feature and your target value. Yeah. We'll describe, sorry, but should we be sure that a split training and test data? We should be sure to have a split of training and test. Yes, we have to. Actually, in many cases, we even split it to 3 parts. The training, test, validation. I think what we do is the training validation is for training. The validation is used for estimate the training error, and the test is used for evaluation. I don't know, optimization the hyperparameter. I forgot about that. It's just one of them is for optimization. The hyperparameter or something. One of them is to estimate the final training error like that. So usually it's more complicated. You have to have split to 3 data set. Yeah, at least you have to have 2 for this simple example. Okay, then I'm going to answer the question from Mukesh. Can you please describe? And then
after that, Jeroen again.
No, I have answered the Jeroen. So describe the output of the last block where hyperparameters are tuned. You mean the? Let me just move this. You mean here? I think this output is just tells you that 0.06 the learning rate maybe is the best. Though I haven't just looked detailed at how this is output. I think it's just directly return you that what is the best choice in this range from 0.01 to 0.5, I guess. Yeah. Though I don't know why it's not giving you that as a search for the other 2, the n estimator or the max depths. They should give you finally give you just the best choice of this hyperparameter. Okay. Yeah, I don't know if I answered, but this is this is what you can print out. I think I just didn't print out all of them. Yeah. Okay.
Okay.
So,
Xifeng, it looks like there are no more questions at the moment. Maybe we can give the participants 10 more seconds to think about questions, or I don't know if Bruce or Ilya have some comments to make at this stage. No, it looks, Xifeng, there are no more questions coming.
Okay, then I still have a little content I'm going to cover.
Okay.
We have a question. So for the hyperparameter optimization,
just came in.
Can we optimize the depths? Of course, that is just we put it here in the maximum depths. Yeah, you can put anything there, but some of the hyperparameter is not sensitive to your training. Some of them is very sensitive. So this need your experience from your daily work, that you know that for a particular problem, for a particular model, that some of them is very sensitive. They should be the first set of the hyperparameter to be optimized. Some of this you can ignore them, right? This is just depends on your experience. Okay, now I'm going to cover a bit of my slides. Hope that you can see my screen, right?
Yes, we can still see it. Thank you.
Yeah, I just have a little words that's about the rho curve we just introduced. So actually, what I want to say is that the rho curve, every single point on the rho curve is equivalent, is equal. So when you train your method, there's not saying that this point is better than the other point. So but actually in our daily, let's say the actual work, how to choose that which point we want. For example, we want to choose signal efficiency 0.70%, and in the same time, background rejection of the background efficiency is 5%. If we want to choose this point, it depends on your exact task. For example, here I give one example. If you want to do a fraud detection, for example, you are working for a bank and you are detecting that if the transaction is like money laundering, or something like that, you do a machine learning of that. So it will label that this guy, this time they're doing the transaction is money laundering like. So then the fraud cases will be labeled as a signal, and the normal transaction will be labeled as background, because the majority part is a huge amount of the transaction is normal. So you just label them as background. You are interested in those very rare particular fraud cases or the money laundering cases. Okay. So then in this case, if your major task, this depends on your major task. If your major task is just to keep the normal transaction as much as possible, you don't want to bother your clients so often. So every day you reject the normal transaction, then you will lose your client. This is something you don't want, right? So you want to keep the normal transaction as much as possible, but to punish some of the very significant fraud. So in such case, you usually just choose the top left, the blue circle here. Your signal efficiency will be very low, but your background rejection will be very high. So that you let all of the normal transaction alone, you don't touch them. But for maybe 10 of the real fraud, you punish the most significant 10% of them, or say 1/10 of the real fraud. So this is, you can just say, threaten that the people who's trying to do the fraud, but you also keep that your normal transaction is not influenced or affected. But if your major task is not this case, for example, like if your major task is to block every single fraud, you don't want any single fraud happens, but you don't care about bothering other normal transaction. Possibly you will choose the working point at here, this point. You get 99% of the fraud detecting efficiency, but possibly you will also, in the same time, you cannot avoid that. In the same time, you will bother 50% of your normal transaction. That possibly you will have some consequence of that. So this is what I mean. Once you have a rho curve, so decide to where you set up your working point, your real working point is really depending on what is your major task. You want to have a higher signal purity, or say to have a lower type 1 error, or say lower false positive probability, or you want to just do not let any single fraud happen, then the choice is totally different. This is what you can see. So this is one additional thing I'm going to introduce about rho curve. That rho curve just give you a general feeling that which method is good, but it doesn't mean that the method has the largest AUC or which is close to this point is the best method. It also depends on where is your major working point. For example, if two curves, they cross with each other, for example, assume that this red curve is inferior to the blue one at this point, but it may exceed the blue one just near this top left side. In that case, if your working point, your usual working area is this region, you only need to consider that this region, you don't need to care about, say, the red one is inferior to the blue. So I choose the blue. You just look at this region. Maybe in this region, the red one is better. That's possible. Okay. So for another example is like the face recognition to unlock your phone. So you would prefer to tune your model to have the minimum false positive so that other people cannot unlock your phone easily. But the price for this activity is that sometimes you must try 2 or 3 times to succeed to unlock your phone. So you cannot just do it just always from one time. But this can protect you from other people can unlock your phone. Okay, so but just do 2 or 3 times to unlock your phone is acceptable. So this is just to actually decide that where you choose your working point is really depend on what you are doing, what you're exactly doing. And then the summary for today is that the take-home information is that the principle of the machine learning optimization, you have to keep in mind 2 things. One is the rho curve. The better rho curve or the better local rho curve, then the best machine learning, say the result you have. And the smaller overfitting, overtraining, the best, or say the better generalization of your model, then that means the method is better. So basically you have to consider both of them in the same time. Okay. Okay, then the last thing is about overtraining, like just emphasize again, that's what overtraining means. Like, for example, to split the circle and the cross. You can do the first model, which just draw a line, this black dashed line, like this way. We can say that this is a reasonable fit, also a reasonable model, but it falsely categorized the cross to be the circle region. So this is some kind of a confusion, as we have mentioned. And this method that uses a blue dashed line and they just twist it in here. So this method just categorizes 100% of the circle to the circle area, and all of this cross go to the cross area. So that has better discriminating power than the first method because there's no false categorization in your training. But assume that a new random test sample is joined like this green circle, and it's put here. Then for the first method, this green circle will be labeled as the circle, so it's correctly labeled. But in the second method, this green circle will be labeled as a cross because it's on this side, on the lower side of this bottom side of this blue dashed line. So that means though the right side method has better performance in the training data set, but it doesn't mean that it's necessary to have the better discriminating power in the new random test data set. So this is just a concept of how to understand the overtraining or the generalization. You hope that you use a moderate model, also the fitting method, to mostly separate the 2 different data sets, but also have some tolerance for some exceptional cases. Okay, not just separate every single events. And another example, let's say that if you use only 4 images to do the categorization in the training, it's a cat, cat, dog, dog. And in the classifier, maybe the classifier will think that the dog should have a large area of white color because this is white and this is white and this is yellow and the other color. Then you use a new test sample of white cat, go into it, and maybe that the classifier will say that, okay, this is a dog because it's more like a white color, right? So this is something you want to avoid for your classifier, that to be more generalized, it's not just taking a particular feature for a particular case in your training data. Okay, that's all for today. I hope you can just take home that this information is very simple criteria. Okay.
Yeah, thank you very much, Xifeng. It was again an excellent lecture, and I think every participant will have learned a lot. So thank you very much for that. Let's wait a few seconds to see if we receive some questions or feedback from the audience. And again, please use the Q&A or just raise your hand, and we can give you the right to speak. I'm not sure if Bruce or Ilya would like to make some final comment on this double lecture while the participants think about possible questions. No, it doesn't seem.
Yeah, Dr. Ruan has a lot of experience in this kind of tutorial, so I hope that people can go back and there's a YouTube link, right? That
Yes. We will. We've posted the slides and the YouTube and the videos, or not this one. This we still have to download, but it will all be. You will all find the link to the NITheCS website. Yeah.
Sure.
So then, if there are no urgent questions, thank you very much, Dr. Ruan, for the excellent double lecture last week and today. And thank you, Bruce, for being with us this afternoon. It's really much appreciated. And and we are looking forward to meet everybody again next week for the last lecture in this series by Professor Mellado. Yeah. So thank you very much, everyone, and have a good rest of the week. And we will see you again next Tuesday. And thank you, Ilya, as well. Thank you.
Thank you.
Thank you very much. All the best.
Thank you.
Thank you.
Bye-bye.
Thank you very much.